Hello! In our next section, we will continue to talk about properties of light. Specifically, we'll talk about how light is polarized and how this relates to the long-standing notion of the birds and the bees. So what we can say is that some eyes, for example, eyes that might be possessed by birds or bees, are sensitive to the manner in which light is polarized, that is, to the plane of polarization. Sometimes in class, I bring a bow and arrow, and I make this kind of a demonstration. Today I'm going to use a simple ruler as if it had been my bow. And what we can do is we can say that most of the time when we're shooting a bow, we hold the bow kind of like this. We grab the string this way, we pull it back, and we let the arrow fly. We can think of the tip of the arrow in this demonstration as being a photon of light. And what we're going to see is that some birds and some insects are actually sensitive to the plane of oscillation in which that photon of light might be moving. So if I have my bow just like this, it's vertically oriented, and I pull back and I let my arrow fly with its photon on its tip. As the photon is moving from the sun to the earth, moving in this video a depth plane, which would be from where I am to where you are, that photon of light might be oscillating as it's moving in the z-plane or depth plane. And in this particular case, I'm holding the bow like this vertically, and the plane of oscillation in this hypothetical will also be vertical. So the photon is moving up and down kind of like this. In American baseball, sometimes people will talk about how a curveball will break downward right near the plate where the batter is. So the ball's coming straight at you and then breaks this way. That would be a vertical kind of a break, and consistent with this vertical plane of polarization. Light can be polarized along this plane. We might have more of a horizontal orientation. I can now pull my hypothetical bow back, let the arrow come flying, and now what might happen is maybe the photons are coming at you in this way. That is to say, even though they're moving from me toward you in the z-plane, it might be the case that the individual photons are now oscillating from left to right. There is now what we might call a horizontal plane of orientation as opposed to this horizontal plane. Okay? So light can be polarized in these different kinds of planes. And some birds and insects have the capacity to pick that information up. You and I can see colors, so we're sensitive to the different wavelengths of light. We can also respond to different intensities of light, which would correspond to the number of photons that we have. But you and I typically are not sensitive to the plane of polarization. And this is not just true for humans, it's true of other mammals. So-called higher vertebrates typically are not sensitive to the plane of polarization, unlike the birds and the bees might be. So what we're going to do in class is a demonstration that I'll begin here. We'll be using some different polarized filters. Some of you might have sunglasses that work by polarizing or by polarizing filters. We're going to show you in class some polarized filters, and we'll have you take one of these filters, kind of like this, might look something like that, and we'll have you place it in front of one eye, and then take a second pair of filters and have you rotate that second pair of filters in front of the other filter. So typically I like to have my students grab this in their left hand and cross over and cover maybe either the left eye or the right eye. I'm going to do the right eye here. Our instructions have various ways of doing this. I'll keep this eye covered. I'm going to take a second filter, and I'm now going to put it in my right hand, and I'm going to put the two over top of each other and begin rotating them as I'm looking through the filters. And I'll let you have the experience in class of seeing what this is like, but hopefully this will give you some notion of how polarized filters work. So what's happening with these polarized filters? On a given pair of filters, one filter blocks a certain plane of polarization. Going back to our bow and arrow demo, maybe one plane is blocking vertical planes of polarization, or one filter, excuse me, is blocking a vertical plane of polarization. It might be that our second filter is blocking the complementary planes of polarization, maybe the horizontal planes of polarization. So we can think of the light passing through. The photons are now moving through my fingers, which are vertically oriented. I can have a second filter at that same orientation, or I can rotate that such that I now have one filter blocking out the horizontal plane, while the other filter is blocking out the vertical plane. So by properly orienting the two polarized filters, we can block either all the light, and we probably can't get all the light in these relatively inexpensive filters that I've obtained for probably about 75 cents each, but you get the idea. We could orient these filters, and if they were complete filters, we'd be able to block out all of the light. In this diagram, what we're going to show you is how these filters are working by way of graph. And on this graph, we have the plane of polarization on the x-axis. Okay? So we can have, for example, orientation A, which might be my vertical orientation. And then over here, we'll have some orientation 90 degrees away. That might be my horizontal orientation. On this axis, we're tracking the number of photons. This would be a lot of photons. This would be few. I'm using the number 100 here somewhat in jest. We have far more than 100 photons, but you get the idea. Here's a lot of photons, here's none, and these are intermediate levels of photons that we might have. When we have no filter in front of our eyes, all the photons are coming in. Okay? So there's a complete passage of all photons into your eye, but what we can do is add a particular filter in front of your eye, maybe just one at a time. And this filter now will allow certain planes of polarization to pass through, kind of like the vertical orientation, for example. The photons that are coming at you with this kind of oscillation will make their way on through. We could draw a straight line down and over, or we can have a slanted line and over. The point is, on the right-hand side of this axis, we have this alternative plane, which is 90 degrees away, and very few photons, maybe ideally 0, would be making it through in this particular case. So rather than getting the full complement or the full ensemble of all possible photons, we're getting just a subset of those photons in this case. And this filter now blocks, it allows plane A to pass, but it's blocking the perpendicular plane. We can have a second filter, which will have now the complementary kind of profile. In this particular profile, we have a filter that blocks plane A, but passes the perpendicular plane. Okay? So here now, it might be the case that, for example, the horizontal polarization planes are making their way through. Okay? And if we have the two of them lined up, one in front of the next, and they're properly aligned, we can block nearly all of the light. Now, the way I've drawn these here, you might imagine that we would have had a little bump right here in the center. That is to say that we didn't block all of the light at that particular orientation, and we didn't block all of the light at that particular orientation. So I could draw these in such a way that I might have a little bit of a blip right in the center here. But you also could draw these planes of polarization and the filters such that we have just a vertical line coming right on down here. And we would actually wind up with this flat line, leaving none of the light passing on through. Okay? So those were polarized filters. There are other types of filters. We'll have a demo on smoked filters in the classroom. And what we'll have you do is put one of the smoked filters in front of your right eye, for example, and take a second filter and begin twisting that in front of your right eye. And we'll ask you, what kinds of things do you see? Typically, you come to the conclusion that orientation does not matter in the same way for these smoked filters as it did for the polarized filters. So we might ask, what's going on with these smoked filters? On the first pair, your filter partially attenuated all of the planes of polarization equally. So rather than having some planes pass and others not pass, we had all planes of polarization, whether they were vertical, horizontal, or one of these intermediate levels. Okay? All of those would be blocked, but only to a little bit. Your second filter does the same. It attenuates whatever is remaining from the first filter. Again, all planes of polarization are equally attenuated or reduced. That's what we mean by attenuated. Unlike the polarized filters, orientation makes no difference for these smoked filters. So let's take a look at what that might look like here. This is the same axis layout that we had a moment ago, and we start out, as always, with no filter. And then what we can do is we can say that we put on a single smoked filter. It attenuates all planes equally, and by toggling from here to here, we see that attenuation from here down to here. And notice that rather than having some kind of a profile-specific blockage, we're really attenuating all axes of orientation or all planes of polarization equally. We can now add yet another filter, and we will now begin filtering out whatever made it through the first filter and so forth. So we wind up the same way with these smoked filters as we had with our polarized filters. But the difference is that we get there through two slightly different mechanisms and two very different kinds of profiles. Now, an important point about all this is the following. If I placed just one of those filters in front of you, you wouldn't be able to tell which filter it was. Basically, each of these two different varieties blocks out the same number of photons, but they do so through very different kinds of mechanisms. You could not determine whether A, the light was reduced equally across all planes of polarization, or B, the reduction was polarization plane specific, if I might use that phrase. And this is because, as a mammal, you're basically polarization blind. Okay? Not all animals are polarization blind. Some animals, like birds and bees, are able to use the plane of polarization, and they're able to pick that information up, and they might sense that. Now, who knows what that's like to them phenomenologically? You and I experience different wavelengths of light as different colors. Maybe birds and bees experience different polarized planes as different colors, or they have some other kind of phenomenological experience, but we can show through experiments that various kinds of animals are able to pick up the polarization plane. In principle, sensitivity to the plane of polarization could be used by birds or by other animals to guide their navigation over very, very long distances. Okay, so what we'd like you to take away from this component of today's discussion is we'd like you to be able to draw a luminance by polarization profile for polarized filters, and you can back up the video if you need to see what those look like. Make sure that you have your axes appropriately labeled with photons on this side and your plane of polarization on this side, the x-axis. Be able to draw the luminance by polarization profile also for the smoked filters. And this will give you a really good sense of how these different kinds of filters are working. We'll give you a moment to do that. Okay, if you'd like to now proceed, we'll go ahead and we'll talk a little bit about the human eye. Recently, we've been discussing different properties of light, the different advantages that we have in being sensitive to planes of polarization or not being sensitive to planes of polarization, the consequences of that. We've talked about other properties of light. We've talked about how fast it moves, the fact that it moves in straight lines and so forth. Now we'll begin to really zoom in on the human eye, and we'll talk about physiological optics. So here's a cartoon of the human eye. And the eye is said to have two optical components. These two optical components are the cornea and the lens. Just to give you a little bit of background, we sometimes talk about how a person might be optically blind, and what we mean by that seemingly redundant phrase, optically blind, is that there's something wrong with the front end of this person's visual system, something typically related to the eyeball. Persons can be blind for other reasons. Your eyeball might be just fine, but it might be the case that there's something going on cortically that's broken. It might be the case that you've had a stroke and you've now had a lesion to some important neurons in your occipital lobe. It might be that some of the nerves that carry information from the eye through the thalamus, that relay station, back to the occipital lobe, maybe those connections are broken. So people can be blind for any number of reasons. When we talk about optical blindness, we're talking about some kind of limitation here at the front end. And we can talk about these two particular kinds of optical components, the cornea and the lens. Okay, information, or I should say, image formation on the retina depends on these two different components. It certainly depends on the cornea. The cornea refracts or bends light. Now, you might want to emphasize that in your notes, that to refract is to bend. Okay? So typically light is traveling in a straight line, but when it comes to some kind of an object like the cornea, we have the light being bent in a particular way. We change the direction that the light is entering the eye. Because the cornea is convex, and I'll show you what convexity means in just a second, it makes incoming light rays converge to a focal point. So here's a simple sheet of paper, and I'm going to bend it toward you. That would be a convexity. Noses are convex, breasts are convex. Here's a convexity, and we can have convexities of varying magnitudes. This is a strong convexity, this is less strong, that's less strong still, and so forth. So your cornea is a convex lens. It's going to refract or bend light. The refractive power of the cornea, or any other optical device, is measured in a new unit that we call a diopter. And specifically, the human cornea typically has about 40 diopters of refractive power. So let's see if we can understand what the diopter is. Here's the diopter spelled out, and we can define this mathematically as being equal to 1 over the focal length in meters. But now that we've introduced focal length, we have to define that as well. Focal length is the distance from the optical device, that might be your cornea, for example, to the focal point. Okay? And the focal point is going to be back here. In the case of the eye, the focal point will be the retina. The retina is going to be what catches the photons of light, and we're hoping that the cornea, or whatever kind of optical device we have up front here, can help us bring into focus all of the photons that are coming from whatever the light source might be. So here might be the cornea, this side might be the lens, and in between we have a focal length. And we can express the strength of any given lens that's going to help us bend the light in terms of diopters, where the diopter is equal to 1 over the focal length in meters. So we mentioned a moment ago, the cornea has a refractive power typically on the order of 40 diopters. We also mentioned that the cornea is just one of two optical components, optical being a property of the eyeball. The other one is going to be the crystalline lens. So image formation depends in part on how strong your cornea is and its convexity, but also on the crystalline lens. Now here's how the two are different. Unlike the cornea, the crystalline lens can change shape. Your cornea is whatever shape it is, and it typically is worth approximately 40 diopters, but it doesn't change moment over moment. By contrast, the crystalline lens can change shape, providing either greater or lesser levels of convexity. And as it's changing from a very convex shape to a less convex shape, the number of diopters that it is offering will change. And it typically changes on the range between 10 and 30 diopters in young students typically your age. This variability in lens shape is called accommodation. So sometimes we lose the capacity to accommodate when the lens begins to harden. It might get stuck more or less at one particular level, or perhaps over a limited range of convexity. So instead of getting a 10 to 30 diopter range, we might get an abbreviated range of some variety. Okay? Together, the cornea and the lens provide refraction ranging on the order of 50 to 70 diopters, at least in healthy young people like you. So we get some refraction that happens from the cornea, that's a constant, and then we get this variable accommodation, the ability to accommodate or to tend to different kinds of refractive needs as you're looking at things that are relatively close to you and things that are more distant from you. Okay? So let's take a look at some kinds of refractive errors that you might be familiar with. And when we talk about a refractive error, we're talking about an error or a mismatch in how light is being bent when it's en route to some kind of a target. One commonly known condition is called myopia. You might say in the adjective form that somebody is myopic. I myself happen to be myopic. I'm a 4-diopter myope. This is a form of nearsightedness. The eyeball is essentially, if you will, too long given the refraction that we have on the front end of the eyeball. Again, that's going to be the cornea, and a little bit posterior to that we have the lens. Okay? So here's the light coming in. Light is traveling in straight lines until it hits the lens when we begin to bend it, depending on the magnitude of the convexity. And in this particular case, you can see that the light is being bent to a focus, but the retina is back here, and the light is now being brought to a focus a little bit sooner than it should. And by sooner, I mean short of the target. So here's the target. Ideally, that point would be right back here. But given this refractive power, it's almost as if the eye is refracting that light in a manner that's too strong given the length of the eye. Another way of saying the same thing is that the eyeball is, in effect, too long given this level of refraction. So we can correct this. We can reduce the strength of that refractive power by adding some kind of a negative lens to it. So this can be corrected with a concave lens. We can put a lens in front of the eye that bends the other way. This would be now a concave lens versus a convex lens. And this will now weaken the refractive power. And so these will not be bent quite so strongly. They're going to be bent a little less strongly so that now we make contact more precisely with the retina. The point of focus will land more exactly on where the retina is. We can also have the opposite kind of refractive error. We might call this hyperopia, and we might say in adjective form that a particular person is hyperopic as opposed to myopic. Okay? And this would be the example of farsightedness. So in this particular case, the eyeball is essentially too short given the refraction. So here come the photons of light traveling in straight lines, as they always do. We have now the bending of the lens, but this particular lens is not bending the light sharply enough in order to hit this particular retina. So what we'd like to do is take this refraction and increase it by adding some kind of convexity to it, and we can now correct this with a convex lens, increasing the strength of the refractive power by adding a positive lens. So positive lenses will be convex, negative lenses will be concave, and by putting this in front of your eye, we can correct your refractive error and make it go away. As we get older, typically by the time we're 40, most people suffer from what we might call presbyopia, and the adjective form of that would be presbyopic. So we can talk about a presbyopic eye, and this translates from the ancient Greek to mean old sight. Presbyopic, old sight. And again, this happens to most of us by the time we're in our 40s. It's caused by sclerosis or hardening of the crystalline lens, a reduction in the refractive flexibility that we have. So maybe the lens starts to harden and we don't get the full range that we used to when we were a little bit younger. Okay? So we can think of this as a form of sclerosis. Some of you know about atherosclerosis or hardening of arteries. This would be a hardening of the lens, making it a little bit less flexible. Now the way that we correct this typically is with bifocals. For reading, we might have some correction with a strong convex lens. So on the bottom half of your parents' or your grandparents' glasses or bifocals, we have a really, really strong lens that can help refract or bend the light that we need to bend from close distances. When objects are further away, though, as we move the object further away, the light will be traveling in straight lines, and we might need a little bit less refraction in that case. So we can have now correction with a weaker convex lens. So we can now have some stronger or weaker convexity added to whatever is going on in our cornea and our lens so that we can recover some of the flexibility that we used to have when we were younger. So this is how we typically treat presbyopia, the adjective form presbyopic. Okay, so in class we'll do a demo on lenses. We'll pass the lenses around. A 3 diopter lens will be positive 3 diopter lens will be a convex lens, okay? And that will increase refractive power. A negative 3 diopter lens will be concave. It will decrease refractive power. It's a nice property of these lenses is that they're perfectly linear. You can take a positive 3, a minus 3, put them right on top of each other, and you look through that just like you would look through regular glass, and you'll see no change in refractive power. So these are perfectly additive. They're going to actually cancel each other out with the positives offsetting the negatives. Okay. We can talk about how image size is measured on the retina. We'll assume now that we've gotten the refraction right, that the cornea is refracting light about to a proper level, that the lens is refracting light to a proper level, or that we've added some kind of adjustment maybe by a contact lens or by reading glasses or by bifocals. Now let's talk about how the image size on the retina might be measured. Size or retinal subtents, we might say that an image subtends or occupies a particular region of the retina. We express this in degrees of visual angle, very much like what you might measure with a protractor. Okay? If a 1 centimeter long stimulus is viewed at this distance, 57.29 centimeters, okay, the stimulus subtends or occupies 1 degree of visual angle on the retina. And 1 degree of visual angle will correspond to approximately 300 micrometers, that's millionths of a meter on the retina. So these are very small units of space. They are not as small as the billionths that we talked about earlier when we described nanometers, which is 1 times 10 to the negative 9. A micrometer, shown here, will be a millionth of a meter, that's 1 times 10 to the negative 6. Okay? So 1 degree of visual angle corresponds to approximately 300 micrometers. If you have an object out there in space that's 1 centimeter this way, okay, and you're 57.29 centimeters away from that, that's going to cast an image on your retina after it's been refracted that will occupy approximately 301 millionths of a meter on your retina. We call that 1 degree of visual angle. So let's see where that comes from. Visual angle can be measured according to this formula. This is a function that we have. You might remember in high school learning about linear functions and nonlinear functions. You might remember certain trigonometric functions, one of which is the arctangent function. Okay? The arctangent is the inverse of the tangent function. Okay? We use the arctangent when we know the lengths of interest, but we need to find the angle. So it might be that we know how far we are from a stimulus in terms of centimeters. It might be that we know the left-right expanse of that stimulus in centimeters. We might know the vertical expanse of that stimulus in centimeters, but we want to know the angle on our eye. How many degrees of visual angle? So what we would do is we would take the arctangent of a very simple ratio. The denominator of that ratio will be the viewing distance. Frequently in vision science, when we're running laboratory experiments, we try to position the person 57.29 centimeters away from the stimulus. And the stimulus size will be whatever it is, expressed again in centimeters. So we have some centimeter stimulus over some viewing distance expressed in centimeters. And that ratio now can be within our parentheses. We'll take the arctangent of that ratio, and that will give us the visual angle. Here's a simple rule of thumb, and here's one of today's bad puns. For our rule of thumb, we can say that your thumbnail, left to right, extended at arm's length, will occupy about 1 degree of visual angle. Some students will object to this and say, but my neighbor has a bigger thumb than I do. My neighbor on the other side has a smaller thumb than I do. But remember that people with smaller thumbs tend also to have shorter arms. People with bigger thumbs, on average, will have longer arms. So thumb width and arm length will tend to co-vary, and this is not a bad heuristic or rule of thumb. If you'll now stick your thumb out all the way and look at your thumbnail's width from left to right, that will occupy approximately 1 degree of visual angle. Here's a fun fact. The full moon will tend to subtend or occupy just about half a degree of visual angle. So we can ask too about the blind spot. Some people know about the blind spot from Intro to Psychology. The blind spot is a perceptual phenomena that arises from the optic disc. The optic disc is an anatomical structure on the nasal side of each retina. So we can talk about the temporal side over here, or the nasal side, the side closer to your nose. And we might say, somewhat jokingly, that it's vulgar to call the optic disc the blind spot. Okay? Those are two different ideas. The blind spot is this perceptual phenomena. The optic disc is actually an anatomical structure. So the blind spot is going to be this perceptual hole in our visual field that's approximately 6 degrees of visual angle in diameter. So the optic disc subtends about 1,800 micrometers on the retina. Okay? The blind spot is many, many moons big. Remember that the moon is just 1/2 a degree of visual angle, and a really fun exercise is to wait for the full moon to come out and do your thumb at arm's length trick. You'll know that that occupies about 1 degree of visual angle. If you then hold your thumb up in alignment with the moon, you'll see that the full moon, even though it seems to loom very, very largely in the sky, can be hidden behind 1/2 of your thumbnail width. That's how small it is, just 1/2 of a degree of visual angle. So approximately 12 degrees or 12 moons would be the size of your blind spot perceptually or your optic disc anatomically. And we'll have in class a nice handout on the blind spot, and we'll do a couple of demos finding our own blind spot. So I hope what you'll do now is stop the video and make some comments on what you find confusing or what you find particularly interesting, and we'll have some class conversation about our introduction to the eye and physiological optics. See you in class.